Now we're going to move on to the last group of problems. The first one we're working on is number 33. Number 33 states that an unwary football player collides with a padded goalpost while running at the velocity of 7.5 meters per second. So his initial velocity is 7.50 meters per second. And he comes to a full stop, so VF. And again, I said I was going to use 0 as initial. So that's going to be 0. And it compresses the padding with his body. So the distance that this full stop occurs is 0.350 meters. Or another way to look at it is F minus X0 is equal to this number. So either way you can look at it, that's the way you can write it down. So the question is, what is his deceleration? Now we remembered that in this previous problem, we saw that acceleration is equal to V F squared minus V0 squared divided by 2 over X minus X0, or 2 over D. And we can put in VF is 0, so V0 is minus 7.50 squared. And the distance will be 2 times this number right here, 0.350. And if we do the math here, we get negative, excuse me, 80.4 meters per second squared. And it's a negative because it's in the opposite direction that he is traveling, or it's a deceleration. Now the second part of this problem is to calculate the time that it takes that to occur. And again, there are a couple ways to do that. One is to say that the displacement, x minus x0, is equal to the average velocity times the time. And the average velocity is the sum of these two divided by 2. So it's going to be 7.50 divided by 2 times t. If we move this number over here, we get 0.350 times 2 divided by 7.50, and that's going to equal the time. If we do the math here, we get 0.0933 seconds to 3 significant figures. So 0.0933 seconds, or 9.33 times 10 to the minus 2 seconds. The next problem is number 37. And number 37 states that dragsters can actually reach top speeds of 145 meters per second. So VF is equal to 145 meters per second when starting from rest, which is V0 is going to be 0, and they do this in 4.45 seconds, so very quickly. Considerably less time than given an example, blah, blah, blah. Calculate the average acceleration for such a dragster. Well, this is pretty easy. The acceleration is going to equal VF minus V0 over t, assuming that this acceleration is constant. So it's going to be 145 over 4.45, and 145 divided by 4.45 is 32.6 meters per second squared in the positive. B states that find the final velocity of this dragster starting from rest, the acceleration found at A for 402 meter quarter mile without using any information on time. Now what they're saying there is if you use this formula, V squared F is equal to V0 times T plus 2 times the displacement X minus X0 times the acceleration that we found up above here. And so if we say, we're going to say that v is going to be the square root of v0, and the v0 is 0, so it's going to be the square root of 2 times 402 meters, times the acceleration that we found, which was 32.6. If we do this math, we get 162 meters per second, which is slightly more than 145. And the question is that why is the final velocity greater than that used when you found the average acceleration? The hint is that we were assuming in this that the acceleration is constant, which is probably an erroneous assumption. Acceleration tends to start slower and increase, because if you assume the force that the engine puts out is the same, overcoming the static friction takes more work than overcoming the dynamic friction. And so the acceleration early on is going to be less than the acceleration later on. And this number representing an average, early in the trip, it's going to be slower than later, but later it's going to be a lot faster. And so in terms of acceleration, and so that's actually why these two numbers are not exactly the same. Okay, the next problem is number 45. Number 45 states, and now we're getting into falling objects. So these problems, from now on, we're going to be talking about objects that are moving in one dimension, but that dimension is in the y-axis. A dolphin in an aquatic show jumped straight up out of the water with a velocity of 13.0 meters per second. List the knowns in this problem. Well, the known is this velocity, and also the fact that g is minus 9.8 meters per second squared. Now, why did I put a minus? Well, his velocity is up and the force or the gravity is down, and so if I make this positive, then this has to be negative. And so that's the thing we know. We also know that when he reaches the peak of his and falls back in the water, at the peak his velocity has to be 0 in order to stop and then fall. And so those are the three things we know. The next question is, once we know that, how high does his body rise above the water? And so we can say that v squared is equal to v0 squared plus 2 times g times the distance that he travels, or if you want to write it as y minus y0, you can write it that way. And since we know this vf is 0, so we know that 0 is going to equal 13.0 squared plus 2 times minus 9.8 times the distance that he travels. And so this is going to equal 169, that's 13 squared, minus 19.6 d. And if we move this to the other side, that means d is going to equal 169 divided by 19.6. And if we do the math here, we get 8.62 meters out of the water. So he leaps 8.62 meters out of the water. Now the third question is, how long is he in the air? Well, we know that d is equal to 1/2 gt squared. And because vf is 0, you don't have to take that into account in terms of the time that he's out of the water. You don't have to use the v0t, because when he falls back in the water, this is the equation that will be governing that. So that's going to be 1/2 times 9.8 times t squared is going to equal d, and d we found was 8.62. And so t is going to be 2 times 8.62 divided by 9.8, and take the square root of that. And if you do that, you get 1.33 seconds. The next problem is problem number 53. Number 53 states, there's a 250 meter high cliff at Half Dome in Yosemite National Park in California. So we have a distance, a y distance of 250 meters. Suppose that a boulder breaks loose from the top of the cliff. How fast will it be going when it strikes the ground? So the first question is, how fast will it go? Well, it starts out, V0 is 0, and Vf squared is equal to V0 squared plus 2GT. 2GD. And so if we move, this is 0. Let me get rid of that line right there, because that's not right. So Vf squared, or Vf, is going to equal the square root of 2 times G times D, or 2 times 9.8 times 250, the square root of that, and the 2 times 9.8 times 250 square root is 70 meters per second. The second question is, assuming that a reaction time of 3/10 of a second, how long will the tourist at the bottom have to get out of the way after hearing the sound of the rock breaking loose, neglecting the height of the tourist, which would become negligible anyway if it hit? So the question is, how long does it take to get from the top down to the bottom? And we know that distance is the average velocity times the time. So the time is going to be the distance divided by the average velocity. And the average velocity is going to be 70 plus 0 divided by 2. And so that's going to be 250 divided by 35.5. And if we do the 750 divided by 35.5, first thing we have to do is calculate the speed of sound. And so this velocity, the first velocity we take into account is the sound, so the time that the sound takes to get down to the person. And so we have to put in the speed of sound in here, which is 335 meters per second. We do that, and that time is 3.75. And we add his reaction time, which is 0.3 seconds, and the total is 1.05 seconds. Then we have to determine how long it takes for the rock to get to the bottom. And so if we put in the numbers for that, we got 2 times D over G. So that's the square root of 2 times 250 over 9.8. And that time is 7.14 seconds. And so he has about 6 seconds to sit there and think about it. And so he has plenty of time to get out of the way. The next problem is problem number 55. Suppose you drop a rock into a dark well using a precision instrument. You determine the time for the sound of the splash to return. Neglecting the time required for the sound to travel up the well, calculate the distance to the water if the sound returns in 2 seconds. So first of all, we're doing this neglecting the sound splash. And so t is 2 seconds to several significant figures. And the distance, or excuse me, what we're wanting to know is the time to the water. And so d is equal to 1/2 gt squared. So that's going to be 1/2 times 9.8 times 2 seconds squared. And so if we do that math, we get this half cancels one of these, so it's 2 times 9.8 or 19.6 meters deep. Now, and it's a negative because it's down. Y is deeper or more into the earth than the Y0. And that comes from a negative 9.8. Now, the second part states that now calculate the distance taking into account the time for sound to travel up the well. In order to do this problem, you have to separate the time. T1 is the time for the sound to come up. T2 is the time for the rock to go down. And T1, 1/2 gt squared, T1 squared, is going to be this distance, 19.8, and that's going to equal the velocity of sound times T2. So that's your first equation. Your second equation is T1 plus T2 is equal to 2.000 seconds. And so the easiest way to do this is to convert everything to T1. And so we say that T1 is equal to 2 minus T2. And then we substitute that in here. Is equal to V times 2 minus T2. Then we use this equation to calculate what T1 and T2 are. If you do that, T1 is 1 point, and this is just math to do this, it's 1.944 seconds, and T2 is equal to 0.0558 seconds. And so those are the two times. Basically, you need both equations because you have two unknowns. The time of the sound down, up, and the time that it takes the rock to go down. And so you have to have two equations, and this is your first equation, and this is your second equation. Then once you solve this for this, then you can substitute and you have an equation with one variable, and you find T1 first and then T2. Now the last part of this is to say what is the new depth given this finding, and all you have to do is now say that the depth of the well is 1/2 gt squared, but instead of using the 2 that you originally used up here, you now use this right here. And if you do that, so it's going to be 1/2 times 9.8 times 1.9442. If you do that, you end up with a depth of 18.526 meters instead of 19.6.